Hi, we have another video on SymPy. The question today is how to do polynomial division for multivariate case in SymPy Python. So the univariate case is f divided by another polynomial. Both of them are in one variable x, and then you have this relation, and degree of the remainder is strictly less than degree of the divisor. What about the multivariate case? I mean, we have more than one variable, so it's not degree on one variable deciding things. And then univariate polynomial ring was a principal ideal domain, so every ideal was generated by a single polynomial. So dividing by one polynomial was enough for you, but in multivariate case, the ideals are not necessarily principal, so you need to have division by more than one polynomial. And then you can see the algorithm and the definition in standard textbooks like Using Algebraic Geometry by David Cox et al. Put this reference. You can pause the video, read this, or look at the book at this page. Also another one, ideals, varieties, and algorithm, again have the same division algorithm in multivariate polynomial. They also provide the algorithm. I assume that you already have seen these things, but you have a little of problem of doing it with SymPy. Some people go do this, not good practice. They write their question in some places and they got some answers. It might be right, but here you see it's a wrong suggestion. Well, there's a page 2, but that doesn't matter. What is a better way of finding the answer is that, well, if the thing that you are using, such as SymPy, is documented, well, going through the documentation. Now, I agree that it can be a pain, and then you do Control F with the word division, and the division that you will find, for example, is this one, which is the univariate case. It takes one polynomial and another one single polynomial. It says generators, but actually it wants one variable. And the keyword arguments that it's receiving, well, according to the example, is just domain on which ring or coefficient ring or coefficient field you want to do the division. And then you can also click on the source and follow up these sub-functions that this div is calling, and you will figure out that it's not the multivariate division. If it was asking for some monomial order, right? If you be a bit more patient and look at each of these things, maybe some of them faster than the others, and some of them you spend a little more time. You go through them, you learn a lot of things, by the way, and then you end up with reduced function. It says reduces a polynomial f modulo a set of polynomials g. Well, it has one of the properties that you want, dividing by a set of polynomials, not necessarily one. Well, it doesn't say division, it says reduce, but let's go more. They have this formula, and then they say r vanishes or r is completely reduced polynomial with respect to g. Looks like a division by multivariate polynomial. And if you have DOP, you can click on source. You look at the function, quick look, you will see that it is extracting order from the keyword argument. If you watch our previous video or you did some Gröbner in SymPy, the keyword argument order equals something is for declaring the monomial order of that computation. If you go to other math software, for example, Matlab, you see they call polynomial reduce for the division, and then you can see the description. It's the polynomial division. It says R cannot be divided by the leading terms of the divisors. That's what you see in the Cox et al. Book, right? Mathematical call it polynomial reduce, and then you may have this question, why they don't call it division or multivariate division? Why they call it reduce? Now, if you look at the Wikipedia page of Gröbner basis, there is one interesting sentence. It talks about reduction of polynomials by other polynomials, blah, blah, until it is sometimes called multivariate division, although its result is not uniquely defined. So you see why some people don't like to call it multivariate division, because that group of people consider uniqueness of the remainder maybe kind of part of the division algorithm. So if you consider uniqueness something that you need to have to call something division, then okay, it's not called division, it's called reduction. But most of people, such as the books you saw for ideas, varieties, algorithms, or using algebraic geometry, they call it multivariate division. So that's totally fine. Now, enough of these things. Let's go for the syntax. Well, here I put the Maple syntax. Like the previous video, I like to do things in Maple to make sure that Python is giving correct thing, and then I can, with confidence, switch doing computations with Python. If you don't have Maple, don't worry, and do not copy paste this Maple syntax in a Python file, because it's not a Python code. I can run it, I have the answers here, and then I can compare with what I get from the Python, right? Two things to note. In Maple, they don't call it division, they don't call it reduce, they call it normal form. So there are more number of terminologies that can be used for same thing in different groups. And the other thing to be careful, if you don't put these single quotes around Q, something happens. The normal form returns the remainder. Here the remainder of this division, f by these two polynomials, is 2. And if you want the quotient, you need to put a name for it and then call that. So q was y minus 1 in this one. And then in the other division, which is different from this one, the remainder was this. And the quotient was y plus x and 1, which is different from this. Now I remove those single quotes, I run this, and you see what happens. What happens is the reminders are fine, but the second quotient is repeated as the same quotient because this q still has the old value in it. So this single quote here is kind of important if you are using Maple. If you don't use Maple, then no worry, just ignore this. Okay. Now going to Python, you should remember this part from previous video when we talk about monomial orders and SymPy. So I'm not going much into that. Now I have several variables. I define one polynomial in 2 variables here, and then a list of 2 polynomials. And one thing, so I see some people use this poly, I don't know, with capital or with a lowercase, class or object of SymPy. It's not always necessary. So for example, what I want to do here, SymPy automatically convert them to SymPy polynomial objects. Okay. Now the syntax for doing the multivariate division is reduced the polynomial that you want to divide it, and then the list or tuple of divisors, okay, and then you give the name of variables for these polynomials that are used here in the order x greater than y here, and then the keyword argument order equal. If you don't put this order equal, it will automatically go with lexicographic, okay. And then if you want to use only graded reverse lex, you don't need to import lex order or monomial order classes from this place. That's why you can ignore this line too, and you use the alias of those 3 orders, same as what I did here. But if you want to define a monomial order from yourself, so I define monomial order defined by this matrix, which is not by default defined in SymPy, then I needed to import this guy, declare a child class of it, and declare an instance of that, and then you put order equal name of that monomial order. Okay, so you have the option of doing the multivariate division with any monomial order that you like, but you may need to define them. Okay, and for lex you can use the alias, or you can import it and define an instance of that and then use the name of that instance. That doesn't matter. Okay, now I run this, I should get the same results as this if it is the true multivariate division, right? Save, run. So here just I showed you two different things. If you want to take the remainder and quotient out, put them a name, you can do that, and the quotient comes first in Python and remainder comes second, and then I in the print statement I change the order. So 2 is the remainder, same as we saw here, and the quotient is y and minus 1, same as we saw here. Then for the rest I didn't took them separately, put name for them, I just said print them in the same order you like. So the remainder is x plus y plus 1, we see here. The quotient is x plus y and 1, we saw here. And you see if I change the order of these two polynomials, but keep f the same, everything is the same, just changing them. The remainder change, the quotient change. That's why they say the remainder of multivariate division is not unique. I mean, it depends to the order of the divisors, but also depends on some other things, such as the monomial order. So here I have this polynomial with 3 variables and these 2 divisors. With lexicographic order, the leading monomial of the first divisor is x square, the leading monomial of the second one is square z. So if something is not divisible by this one, is not divisible by the second divisor as well, and that's the reason you see the quotient for the second one in the lex order as 0. It's kind of useless. But with the different monomial order that we gave, the leading monomial here is still x squared, but in the second divisor will come y cubed. So it's not useless anymore, and you see that the second quotient is not 0 anymore. So I think that's all. Just be careful to not use div for multivariate polynomial division.